Okay, we're going to go ahead and start the radioactive decay PowerPoint. I'm going to split this up over 3 different videos. The first video is more concept, and the second ones are problem solving, more problem solving, and so is the third one. So if you have the PowerPoint in front of you, you also need a calculator so that you can work the problems with me so that we're ready to go. All right, let me go back to the beginning. I don't know why this isn't. Okay, here we go. So radioactive decay, exponential decay. So I don't know how familiar you are with the exponential function, but we're going to get a little bit more experience with it today, and then, or with these videos, and then kind of go from there. So first of all, what you need to know is that when a nucleus decays, it doesn't do that at a constant value. As it decays over time, the rate of its decay will slow down. So it'll be quickest when it's first created. When the nucleus is, if you have a sample that's just created, it'll be very fast decaying, and then over time that rate of decay is going to slow down. So what you're going to end up see happening is that the amount of non-decayed atoms that remain in the sample is going to decrease rapidly at first, and then over time there's going to be less and less of a rapid decrease. So whenever that happens, whenever you have something that the rate of decay is actually changing, and it starts large and then kind of goes small over time, that takes the form of an exponential decay. So that's what that means to be an exponential decay. It's not a constant rate of decay, but rather the one that changes over time and decreases over time. So I don't know how familiar you are with the exponential, but an exponential decay takes this form. It takes the form of y equals y0, where y0 is the initial amount, and then the exponential is e to the minus kt. K is going to be our decay constant. We'll talk more about that later. T is time. So over a certain amount of time, you'll see that the amount that is decayed gets less and less. So if, for example, if you look at this is strontium-90 as an example. After 25 years, it's dropped from 100 grams to 50 grams. The next 25 years, it goes from 50 to 25 grams. The next 25 years, it only goes from 25 to about 12 and a half. So you can see that each 25-year increment is less and less actual decrease in the amount of strontium-90 that's there. So we would say that this is very active at the beginning, because the first 25 years you get a lot of decrease, and then each additional 25-year period you get less and less decrease. So that is what it means to be an exponential decay, so that each amount of time that goes up you get less and less decrease. Okay? So that's the definition of the exponential decay. So one concept that you need to understand is this idea of a half-life. A half-life is the time it takes half of the material to decay. So if you have, for example, if we go back to strontium for a second, the amount of time it took for half the sample, you had 100 grams to begin with, to get to 50 grams took 25 years. To get from 50 to 25 grams, which is another 1/2 of the sample, took an additional 25 years. So we would say the half-life, and the symbol we use for that is a T with a 1/2. We would say the half-life of strontium-90 is 25 years, because every 25 years that happens, half of the remaining sample decays. That's the definition of what a half-life is. So after 1/2, we'd be at 50% of the remaining sample would be, of the parent nuclei would be remaining. After a second half-life after that, you'd be at 25% of the remaining parent nuclei. After another half-life, so after 3 half-lives of time, whatever that is, you'd be at 12.5%. And then after 4 half-lives, you'd be at 6.25%. And you could keep going from that. 5 half-lives, 6 half-lives, each time going down by half the remaining amount. So if we were to plot that, we would say at time 0 we had 100%. At 1 half-life, you're at 50%. At 2 half-lives, you're at half of that, 25%. At 3 half-lives, you're at half of that, 12.5%. 4 half-lives, you're at half of that. So you can see that it doesn't go down at a constant rate, but decays down exponentially. So a couple of examples. You can do this for both the amount of material remaining and the activity, how active the sample is, decays per second. So if they tell you that a sample produces 1,280 decays every minute at one time, and then 4.6 hours later it's at 320 decays per minute, they want to know what the half-life is. So you need to figure out from 1280 to 320, how did we get there? So from 1280, if we go half of 1280, we're at 640. So after one half-life, you're at 640. Then if you do half of that, you're at 320. So that's a second half-life, right? So that means to get from 1280 to 320, we've gone through two half-lives. That's what we've done. And those two half-lives are equal to 4.6 hours. So that means each half-life is 2.3 hours. So to go from 1280 to 640 took 2.3 hours, and then from 640 to 320 took an additional 2.3 hours. So 2.3 hours is the half-life of that particular material. Another example, what fraction of a sample is left after 6 half-lives? So after one half-life, we're at 50%, that fraction or half of it. After 2 half-lives, we're at 25%, or 1/4, right? After 3 half-lives, we're at 12.5%, which is 1/8. After 4 half-lives, we're at 1/16. 5 half-lives is 1/32. And 6 half-lives is 1/64. So that's the fraction remaining is 1/64 of the original. All right, and last one, a sample of carbon-14 is found to contain 6.25%. So that's 4 half-lives. That's where 6.25% happens at. So how old is the sample? So for carbon-14, you have to look up what the half-life is. When you look up the half-life of carbon-14, it's in the back of your book. Let me see if I have it here. I think it's 5,700 and something. Yeah, 5,730 years is the half-life. So I at 6.25%, I've gone through 4 half-lives. So that means 4 times 5,730%. I mean, 4 times 5,730 years. So that's going to be 22,920 years old is how many years that sample's been through if you're down to 6.25%. So that's the general idea behind half-lives, behind radioactive decay. Here's a couple of examples from a graph. The first graph, they tell you to find the half-life from each sample. So if I start at 80, I need to know what time does I get down to 40. So if I trace that down on my graph, it looks like it's about roughly 6 days. Something about somewhere around 6 days for the half-life of that sample. This one starts at 25, 26, 27-ish, so I need to get down to about 13.5 counts per second. So that's roughly here, 13.5. I'll trace that over and then bring that down to here. So that looks like at about 3 minutes or so is the half-life for that sample. So you can find the half-life from graphs, or you can find the half-life from just using basic common sense. The issue lies in that sometimes you're not always given even numbers like we've been doing, where you do a half or a quarter or an eighth or a 16th. Sometimes you're just given random numbers. So we have to have a better way of figuring out how much sample is left after a certain amount of time, assuming that the number isn't always going to be a nice even multiple of a half. So that's where we're going to go to next. So I'm going to stop this now, and we'll go on to the problem solving for the next part.